Okay, this is chapter 25, two categorical variables, and this is the chi-squared test. So this first one here is what we're looking at is goodness of fit. And can be used to determine whether a random variable has some specific probability distribution. So what we have here is we have some categorical variable, and we're going to have so many possible outcomes, and each outcome has a corresponding probability. And then what we're going to do is we have n independent observations from this variable, and we want to test the hypothesis. So the null is always going to be, these are the actual probabilities. And so we're going to work our way and list all of them, starting at the first one all the way to the last one. And then what we're going to do is we have what we expect to have if we have out of n observations. And then we take how many did we actually get of each outcome, and then we subtract what did we expect, and then we're going to take the difference between those and square them, and then we're going to divide that by what we would expect, and this just says add them all up, and then this is called the chi-squared. This is the letter chi in the Greek alphabet, and we just call it the chi-squared, and we're just adding them up over all the possible outcomes. And then the p-value is just going to be to the area to the right. So we're never going to have a less than, greater than. It's just your null is always, these are the probabilities, and your alternative is at least one of these is wrong. And you're always doing right side. So that's kind of nice for these. And it's going to have k-1 degrees of freedom. So it's just easy to go ahead and just show by example. So I want to know if grades follow this distribution. So the probability a student gets an A is 0.25, the probability they get a B is 0.32, the probability of a C, the probability of a D, and the probability they get an F. I want to know if that's correct. So for this one, my null hypothesis is going to be, and I'm just using, this is probability of A is in fact 0.25, and that the probability of B is in fact 0.32, the probability of a C is 0.30, the probability of a D is 0.09, and the probability they get an F is 0.08. So that's my null, is that those are the probabilities. So my alternative is the probabilities are not the values above. So we're just saying that this isn't correct for all of them. So then this is what's going on. So then these were my sample results. I had n observed. So I'm going to use O shorthand. In the homework, you're going to have a column with O. So O, we're going to use shorthand for observed. So this is what we actually saw out of 100. If you add up all these numbers, you're going to get 400. So we got 104 A's, 120 B's, 140 C's, etc. Now, if the probabilities are correct, this is what we would expect. So I'm going to use the letter E. So since I have n is 400, and if the probability of getting an A is 0.25, I would expect 25% of that 400 to be what I would expect. So I would expect 400 times 25. So I would expect to see 100. And then I would expect out of the 400 that 32% of them were B's. So that's 128. And then I would expect out of the 400 that 30% of them are C's, which is 120. And I would expect out of the 400 that 9% of them would be D's, which is 36. And then I would expect out of the 400 that 8% of them would be F's. So this is what I would expect to see. So now to calculate the test statistic, you have to work your way. You have to take each expected value and subtract. We have to take the observed. So if I did shorthand, we're going to take the observed value, we're going to subtract the expected value, and we're going to square that, and we're going to divide by the expected, and we're going to work our way down through all of them. So I want to do O minus E squared over E. So when I do it for the first pair, my O is 104 and my expected is 100. So for this one, the first one would be 104 minus 100, square that, and divide by 100. So that's taking care of the first pair. Now work my way down to the next pair. I observed 120. I expect 128. Square that. Divide by what do I expect? And I do that one next. So let's go pink. So for B's, I get this one. Then work your way down. Do it for all the rest of them. So I expect 120 C's. Excuse me. I observed, I'm looking at notes while I'm writing. I observed 140. I expect 120 C's over 120. I expect 28 D's. I observed 28 D's. I expect 36 over 36. And this last one is 8 minus 32 over 32 squared. And so then what I have here is these are the C's. This is what for the D's. And then these are for the F's. And this is the chi-squared test statistic. So this works out to be 23.77. So then now we're going to need to use table F. And I just realized I did not provide table F. So let me quickly do a table F. My apologies. Where is table F? I don't like that one. Sorry for the delay. I should have. So table F chi-squared. Let me do it this way. That's the one. Well, close enough. So for this one here, we had, I have 1, 2, 3, 4, 5. So K is 5 because there's 5 different possible outcomes. So my degree of freedom is 1 less than that, which is 4. And so then what I'm going to do is when I go back to this table, it's just like we did before. I have degree of freedom is 4, and we work our way across, and I see 23.44 goes way off the table. The highest number for row 4 is 14.86. So my p-values up above, these are my p-values. So my p-value is 0.0005. This value is way off the table. So for this one here, because my p-value is so slow, or so small, we're going to reject the null. And since my 2 hypotheses are the null was these are the proportions or probabilities, and my alternative is they are not, my conclusion is we have evidence these are not the proportions as stated. And so that's, let me do another example. So here's another example. So here we have the Master Foods Company says that the following is the distribution of colors for their milk chocolate M&Ms. So 20% yellow, 20% red, etc. And we want to test this claim. So what our null hypothesis is going to be, and I'm just going to do it as, to shorten it, as the proportions are the same as listed above, just so I don't have to repeat it. And my alternative is the proportions aren't these values. and I bought a bag of M&Ms, and these were my observed values. I had 29 yellow, 23 red, etc. These were my observed values. So now, since for this one here, the total number of M&Ms in my bag, if you add these all up, 29 plus 23, 29 plus 23 plus 12 plus 14 plus 8 plus 20, there's a total of 106 M&Ms in this bag. So I would expect 106 times 20. So I would expect 21.2, and it's okay that those are decimals. They don't have to be integers. And I would expect 20% reds. I would expect 10% of these to be orange. So that's 10.6. I would expect 10% to be blue, because those are my percentages. I would expect 10% of them to be green. And I would expect 30% of them to be, which is 31.8, brown. So then to find my test statistic, remember we need to work our way down. So I'll just highlight the first one. We take the observed minus the expected. 29 minus 21.2, square it, and then divide by 21.2. Then go to the next one. 23 minus 21.2, square it over 21.2. And then you work your way down to all of them squared over 10.6, 14 minus 10.6 squared over 10.6, 8 minus 10.6 squared over 10.6 until I get to the last one, 20 minus 31.8 squared over 31.8. And when you work this out, you get 9.31. Let me go ahead and highlight a few of these. Maybe it'll help a little bit. Oops, I keep doing that. Grabbing the wrong one. Let me get my highlighter. So this was the first one. And then how about I do pink for the next one? That's where these came from. And then I've got the greens. That's where this one came from. And then maybe these. And then how about, let's get a different color. Let's go this color, blue, blue, blue. That's where these came from. And then let me get one more color. I'll just go back to yellow, yellow. And that's where these came from. And then when you go to your calculator, you plug them all in, you get 9.31. Now for this one, I have 1, 2, 3, 4, 5, 6 colors. So subtract 1, my degree of freedom is 5. And then from the chi-squared table, you would go to row 5, and you would see that 9.24, 9.31. So this is just like looking at the t-table, that this is where your chi-squared value, that's what this chi-squared value is, falls between these two, which in turn, we end up with the p-value is between these two numbers. So it's bigger than 5, less than 10. So at the 5% significance level, the results are not significant. So we're going to fail to reject the null. We have insufficient evidence for our alternative, which happens to be in context. We have insufficient evidence to say the proportions are different than as stated. Than those given by the company. So this is how we can do these to test to see if a certain distribution is correct or not. So if somebody tells you what the distribution is, we can do a sample and compare what we actually got to what we would expect. This is a chi-square distribution. I will be posting the chi-square table. So then that's one thing we can do for these. Now this is another one we can do. And this is for tests of independence. This is also a chi-square distribution. And we use it to determine whether two categorical variables are independent from each other. So where this is going to do is you're going to still do the same thing where you're going to do the observed count minus the expected number, squared it over the expected. But it's going to be a little different on how we do the expected count. So your data is going to be in a two-way table, and the expected counts come from taking the row total times the column total and dividing by the table total. And for these, your degrees of freedom is you have to take one less than your number of rows and multiply that by one less than your number of columns. So let me go ahead and show it by example. So here we have in Montana University poll classified respondents by whether they lived in the west, northwest, southwest of the state, and their political affiliation, whether they were Democrat, Republican, or independent. And we want to perform a hypothesis test to determine if political affiliation and where a person lives are independent. So my null hypothesis, the null hypothesis is that these two things are independent. So political affiliation and where someone lives are independent. That's the null, that they are, these two variables are independent. So our alternative is that the political affiliation and where someone lives are not independent. So what we're going to do is this is what we actually observe. So these were the observes. We're here. So what do we expect? So what we're going to do is for this one here, we need to take the row total, which is 68, and the column total, which is 84. So multiply those together, 68 times 84. And then we want to divide by the grand total of 202. And you're going to get 28.277. Then we go to the next one over. So if we want to look at this one, we need to do its column and its row and the grand total. So this will be 68 times 78 over 202, which gives you 26257. Now let's go ahead and do the next one for this box. This is its row and column totals. So this is going to be 68 times 40 over 202, which gives you 13.465. Now we go down to the next one, and I want to look at this entry, which is down here. So this is its column total, this is its row total. So this is going to be 84 times 57 over 202, which gives me 23703. Now I'm just going to continue with the rest of these. So for this next entry, I have 78 is the column. The row is 57. The grand total is 202. This gives me 22010. The next one, I have the column is 40. The row is 57. The grand total is 202. I get 11.287. And last one here, the last row, the first entry is it's column 1 times row 3 totals over 202. That's 32,019. Get rid of that yellow. Then the next one here, let me go ahead and highlight that one. We are looking for this entry, so 78, 77, and 202. So 78, 77 over 202. I get 29733. And the very last one, I want 40, 77 over 202. I get 15.248. So these are all the expected values. I'll leave one highlighted for reference. So say we want this one here. That's where I'm getting the 78, the 77, and the 202. I'll leave that one highlighted. So then we have to do the same thing we did before. I have to take, I have to take the observed of 39, subtract its expected of 28.277. So I want to do 39 minus 28277, square it, divide by 28277. So really quick as a highlight, let's do green. I needed to take, for the first box, there's the observed, there's the expected, and I got this one right here, and divided by the expected. So I take the difference, square it, and divide by the expected. And now I've got to do this for all 9 boxes. So really quick, I'm going to have 17 minus 26257 squared over 26257. Take the next one, which is 12 minus 13. I'm working across the top row. 13,465. Now I'm going to start working on the next row. Sorry if I'm making this a little bit small for you. Make it a little bit bigger. So then the next one, I have to take 15 minus 23,703, square it over 23,703. Then 30 minus 22,010. That's 30. Square it over 22,010. Then the next one, 12 minus 11.287. Square it, 11,287. That takes care of the second row. Now the third row, 30 minus 32.019. Square, 32.019. Then 31 minus 29.733. Square it over 29,733. Then the last one is 16 minus 15,248 squared over 15.248. So let me just highlight one other one. So let's go this blue one. This one right here, this 12, this 11, that was this one right here. So I have to do every pair of boxes. There's 9 pairs, I've got to do that. Take the observed, these are the observed minus the expected squared over the expecteds, and I was adding them all up. And when you do that, you end up with 13,849. And the degree of freedom is I have 3 rows. I have 3 columns. So that gives me 2 times 2. So this is going to be my degree of freedom. So then my chi-squared on row 4 of the chi table. And I will post the chi-squared table on my Open Math for you. And so when you look down, you can verify that your p-values end up being between 0.1 and 0.005, which is telling me I have a very small p-value, which tells me I can reject the null. And the null hypothesis, so that the null is that these two variables are independent. So that's telling us we have evidence for the alternative, which is political affiliation and where somebody lives. And where someone lives are not independent. I hope you were able to follow what I did here. You can always stop and go back and rewind as necessary, and feel free to contact me with any questions.